Good afternoon. Thank you all for coming to the first SETI talk of 2017. Our speaker today is Norm Sleep. Norm was educated at Michigan State University and MIT. He has been studying early life and early planets since the 1980s. Among the topics he's worked on are astrobiology and planetary quarantine, which are near and dear to some of us here at the Institute. Today, his topic is the Late Veneer and Earth's habitability. So let's welcome Norm Sleep.
Thank you. And for people in the audience that are not familiar with the Late Veneer, it's basically a way of tracing how many asteroids hit the Earth after the Earth was more or less formed in its present condition. And I'm obviously large asteroids, one just 10 kilometers in diameter, wiped out the dinosaurs. For life as a whole, microbes, some of them had a real bad day, but it didn't endanger life itself. We had obviously had ancestors that survived. Early in the solar system, we have much larger objects that might exterminate life on the planet altogether, or might decimate it. And like with the Titanic, there were survivors, so we had a day to remember. We have the organisms on the Earth, if there was a survival bottleneck at that time, the genome, all the organisms in this room, including plenty of microbes, are telling this story repeated a long way with a lot of misinformation, but still something that someone can figure out. So we have the moon. The moon is quite inactive. We have the Earth that is very active. This is Orientali. It's the last big basin on the moon. We see it very well because no other large object, obviously, pretty well pockmarked with small craters. How many people have gone through O'Hare Airport in the last few years? Anybody drive across the Blue Water Bridge at Sarnia? Not as many. Did you see the asteroid crater at O'Hare? You didn't see a darn thing. The Earth has active processes. It's been covered with a kilometer of sediments. Other craters have been eroded. The craters that we see well are ones like the meteor crater that happened tens of thousands of years ago rather than 3.8 billion like this one. This object is probably close to 100 kilometers diameter. This would incinerate everything on land. It would boil off some of the ocean, but would not be a particular danger to life itself. Anything that could give the talk afterwards would not. Okay, the moon here is great because it's so old, nothing happens. It's a recorder of record. The geologic record on the Earth is like a great monastery in a dark age where people have forgot that you can make paper out of trees. And when any information comes out, illiterate people go rip pages out of magazines, mix up, make new paper, and write down new things, and the old information is lost. So this has been going on for 4.5 billion years, and the information we have before 4 billion, a few rock outcrops, get older than that, a few zircons, probably the world's supply could fit in a thimble. So the moon is old. A key feature of the moon is it has a very small iron core. The isotope ratios in the moon are very much like the Earth, both volatile elements like potassium and non-volatile elements like calcium. The moon is also quite dry, and it's deleted in anything that's more volatile than manganese. Manganese is the first relatively abundant element that will condense from a vapor after silicon and magnesium and calcium, the main makeup of the Earth, has condensed. The manganese condensed, but things like potassium that are more volatile than not. And the key point in here is that the chemistry of the moon shows that all this material in the moon, any lunar rock we've seen, shows that it's depleted in elements that preferentially go into iron. But it only has a tiny core that's not big enough at equilibrium to take up these elements. So this is a mystery that's been known since the first lunar rocks, and I'm going to be coming back to this off and on. Okay, how do we form the moon? Old Brand X theories is that the Earth was spinning very rapidly. The core of the Earth forms. It's like an ice skater. She pulls in her arms and she starts spinning very fast because angular momentum is conserved. It, however, does not work mechanically. You do not get a moon from this process. The process does explain this great similarity of the moon to the Earth's mantle, and also explains that the moon's mantle, like the Earth's mantle, is equilibrated with metallic iron. We can capture a small object. This is like hitting a hole in one with a moon that's kind of very strange, having this very small core compared to any other silicate object. It's like being the supreme leader of North Korea, typically has 3 or 4 hole in one in every round, but I don't really believe the reports that well. The hybrid theory here is that we have a Mars-sized object, which I'm going to call Theia, hit the proto-Earth, which I'm going to call Tellus. The two objects collide. We end up with the moon forming mainly from the mantle of Theia and the mantle of Tellus. We eject material from the Earth. We're ejecting material that has the composition of the Earth. So it's doing 1 and 2 here, but doing it in a physically plausible way. There are numerous models of this. It's relatively easy to get this outcome, but definitely not certainty, but easy enough that we don't have to worry about it. Okay, so we'll go on here. And the moon forming impact, Earth is vaporized. We may have a few rocks that are inhabited, they're thrown off, they end up on Mars, or maybe Venus is habitable, then can get back to the Earth. That pretty well wipes anything out to ground zero as far as life. I'm going to get to the aftermath of the impact. We have to go for vapor, the nice conditions we see at the Everglades, so we've passed through every intermediate temperature at the same time. These large asteroids were a threat to life after the moon forming impact, and if we consider the lunar record, we're immediately considering only things that happen after the moon forming impact, and we'd like to see how many and what size asteroids actually hit the Earth, whether they kept the Earth uninhabitable or whether the Earth can survive. And we need really to look at the start of habitability, which I'll say we can't time real well, but the moon is giving us a pretty good sample. Okay, iron-loving elements, I mentioned that already. The word siderophile just puts it into, oops, I have to go back here, puts it into Greek. And we have highly siderophile elements here, the platinum group. These elements are all present in the amount that would be brought in by common types of meteorites. The word chondrite is in the abstract. These are the most primitive type of meteorites, elements that are not volatile, extremely volatile like helium and rare gases. The abundance in the sun ratios is essentially the same. We're using a reference here, normalizing everything to what we think the building blocks are. People sometimes get worried about 10 or 20% here relating to the details of later processes. I'm not going to do that. It's a convenient reference. everything here, more or less within air, has the same ratio of chondrite to the bulk silicate earth. Most of these are in the mantle. It's assumed that the mantle is statistically well mixed. But these amounts here, if we actually had equilibrium in iron, would be a couple orders of magnitude lower. And also, it's highly unlikely that the fractionation of these elements into iron would all be exactly the same. The fractionation depends on exponentials of free energy. We'd expect differences of factor of a few in here, but they're all essentially the same. So this pretty well tags this as a mechanical mixture. If we look at moderately silicophile elements, we add in 0.01 to something up here on a log plot. We really can't see it. Whether we get 0.015 or 0.007 or something depends on the partition coefficient. These elements, other than for a minor later addition, are pretty well in equilibrium with the iron of the core. So we have the Earth equilibrating, mantle equilibrating for core, and then this little bit of material making up somewhere about 0.5% of the weight of the mantle of the Earth getting added in later. It comes in later. There was the idea way back when, where the material would come in small objects. You'd go out every day and sweep off asteroid dust, and if you waited long enough, it would pile up real deep. And we, oops, one I want to hit is here. The Earth has an equivalent thickness. If we take all the volume of all the material at a reasonable density, spread it out all over the surface of the Earth, it would be about 5 to 20 kilometers thick. The moon got cheated. If we simply have asteroids coming in, they come in relatively fast. If we have a large difference here in the numbers, the moon may get a factor of 2 less than the Earth, but it's not going to get this huge difference here that gets up to a factor of well over 20. So we generally record these things in these equivalent surface areas. Of course, they hit in large objects, spew over, get mixed up with ejecta, stuff gets subducted with plate tectonics. It's now pretty well thoroughly mixed into the mantle. This is just a convenience, rather just like the normalization here is a convenience, so we don't have to remember the absolute numbers of parts per trillion of odd elements. We simply normalize everything and it becomes a lot easier to think about. We go on here and there are a couple ways to get this. One is that we have the objects that impact the Earth at a size number distribution, so we only have a few large objects. Statistically, the moon will get hit with about the 15th larger object. The moon is smaller, it has less gravity. If you have the woods full of drunken hunters, the deer is a lot likely more hit than the rabbit. No more physics than that. But if we only have a few large objects, the Earth is going to get hit most of the time with these large objects. The probability of the top 5 or 6, 10 large objects all hitting the Earth is pretty large. We end up here with about 6 objects large enough to vaporize the oceans of the Earth. And we're really considering conditional probability after the fact. As you all know, the chance of getting all 13 spades in bridge is the same as getting any random bridge hand, but you kind of look at the 13 spades as unusual. So we have to be careful here, and having the moon destroyed maybe a third of the time in numerical simulations of the accretion is acceptable because we still have the moon, and having it have a chance of 2/3 of surviving. There have been models of the migration of Jupiter and Saturn in the early solar system, and the chance of the Earth surviving it may be about 1%. Then you get real worried about invoking anthropic principles that we have to be here to observe. And if you get out to chances 1,000, but you don't do this in an inane way, like you don't say the Earth's veneer is 5.67843 kilometers, and say it's, if you could measure it that accurately, and say there's a very little chance. So you just have to use common sense, and it's not infallible. So we'll go on here. The second solution here is that this so-called veneer component is really not a veneer. We're stuck with the term veneer. It's too entrenched in the literature. It's like an early star being a bright star, which doesn't go the way of the main sequence. We're stuck with it. We have the Lunar Car, and I'm going to go through the mass balance and stuff, but the excess material that we have in the moon in iron includes the core, and there's excess iron in the lunar mantle. We have plenty of moon rocks, enough to measure that. And if we get almost all of this platinum group veneer from the core of Theia, then very few asteroids hit the Earth. On an unlucky day, the Earth may have been hit with only one object large enough to leave only heat-loving organisms, which in many constructions form a root to the life we actually see. So there is some biological implication for this. So we'll go on here, and we'll do the iron mass balance quickly. I put everything into 10 to the 21st kilograms. The moon's core would be about a 700-kilometer diameter minor planet if it was free and didn't have the moon around it. So it's not a small object, it's just small compared to the moon. Having something that big come in as an iron asteroid later is pretty much of a fairy tale. So we can add up, oops, I keep hitting the wrong button here, trying to hit the light. We have the iron core. The diameter of the core is well known. The density of it's not known. I've said it's iron. We also have excess ferrous iron in the moon. Moon rocks are much richer in ferrous iron than equivalent lavas would be on the Earth. And there's some slop in this, but there's an excess kind of comparable to the lunar core. And again, rounding, we have an excess like this. And we have the Earth. The excess that we can see is this late Veneer. And again, there's slop in here. The point is this number is about the same as this number. Okay, to get this, we have to do a little bit of chemistry. The moon and the disk had excess reduced iron. When the moon condensed, some of the metallic iron reacted with ferric iron and with water as the main oxidants to form the excess FeO. The rest of the iron, these oxidants were used up. We couldn't do any more oxidation. Entered the lunar core and swept the moon free of any of these highly siderophile elements. So we get a clean Veneer component that actually records what asteroids hit the moon. About a factor of 2 of slop in it, but it's definitely much smaller than the moon. The Earth's mantle had excess ice. It's bigger compared to this number than the moon is compared to this number. we're dealing with like 0.5% rather than 2%. The iron got oxidized. Once it gets oxidized, the platinum group elements stay in the mantle. And this would tell us that the moon water is the Earth's water that we see lots of it coming down today, mostly came in before the moon forming impact and predates the moon. Some was lost, maybe in the impact, maybe an ocean of it. If the impact cannot occur, there now be Pikes Peak boat tours. Again, the ways to get at it with the stochastic approach of a few big bodies. We need to explain the excess FeO. Oh, the mantle of Theo was iron rich. We don't know much about how things accrete. This is not going to bother anybody. It's very hard to get the lunar core. The lunar core is a huge body. We'd have to have an iron asteroid that we don't see any like it hit the moon, stay intact when the moon was still, well, not chemically react with the moon. So getting the lunar core from the core of Theia is a process of elimination, but it's a least astonishment hypothesis. We also, the present mantle of the moon, we have plenty of water outside today. For us to work detailed geochemistry, the Earth's mantle has to be reduced at the same time, swept to platinum group elements, and then everything added in the veneer. And we have to also bring in the Earth's water. The Earth's mantle is mildly oxidized, and this, as we'll see, ends up being another problem. Okay, the Earth in this stochastic scenario, big objects hitting, is getting its water late. We have to get the whole ocean of it. That's not a small amount of water. We also have water lost to space to oxidize the mantle, oxidize the material that comes in, and we can't, to have the water arrive early, there's no particular problem. Asteroids, even the so-called anhydrous ones are actually hydrous. There's no problem getting an ocean of water, but getting it late is a real problem. In case anybody is thinking about comets, if I drink a glass of water, probably about this much comes in the comet. The isotopic composition of comets is bad, and we also have other problems. The comets would bring in way too much rare gas. We have way too little krypton and xenon and argon-36 in this room to have this. So the chondrites, if you actually look at them in detail, which people do regularly, are actually altered metamorphic rocks. They're like rocks that are weathering at an outcrop on the Earth. They're a thin hydrous layer on the top of a much larger object. If you're bringing in large objects, these objects are going to get hot early in the solar system on the inside, like Vesta did. The inside is going to be anhydrous. It's a royal problem to bring in an ocean of water. And again, the comets, even if the material was not retained by the moon, the comet vaporized the material ejected to space, it would still pulverize the surface of the moon. It's been known from back really before Apollo, but definitely after Apollo, that most of the moon, the upper crust of the moon is still there. The moon has not been, looks pulverized, shallow is pulverized, deep is not. So again, we drive another nail into the coffin of comets bringing in the Earth's water that we see there. Okay, just to reiterate the impact, I'm going to get to habitability. If we're worried about modeling, the moon condenses quickly. Most of the projectile core in all these models goes and mixes with the Earth core. Think a 700 kilometer diameter object to form the lunar core, that much mass would be resolved. It just barely is in the models, not enough to be a predictive way to model exactly how the Earth-Moon collision occurred. Again, the partition here, we partition iron from Thea's core both into the Moon and into the Earth. We can see it in both places quite well, comparable mass. Okay, we're going to go a little bit now into isotopes. I have plenty of time to do that. We have samples of Archean rocks. These are black shales, as I'll get to in a minute. By 3.8 billion years ago, it's basically business as usual at the Earth. I mean, we couldn't live there. There would be no oxygen for us to breathe. Too much UV would coming in, we get sunburn. But for life as a whole, it's not bad. One of the strategies is to find very ancient rocks that have been isolated like these for 3.8 billion years from the environment. They may preserve heterogeneities that have been homogenized by the very active processes on the Earth. Well, we have a lot more modern rocks, so people do both. Again, the Thea material, if a veneer, the platinum group elements, and all the other asteroid-like material, silicate material from Thea, all get mixed into the Isle of the Earth. They're mixed in this dynamic process. They're mixed in chemically into a mantle-like magnesium rich. Olivine is Mg2SiO4. It's the most magnesium silicate in the upper mantle. And when these rocks melt again to form a new magma, which we can sample, which has occurred for the last 4.5 billion years on the Earth, the material will come from a domain that is enriched in olivine, which will carry around chemical signatures. Just quickly here, if you're worried about the composition of what mixed in, the mantle of the Earth is hot. Any hot magma, if you get a lot of it, like at a spreading ridge here in Hawaii, forms a magma chamber. And even though the magma that starts up here is very magnesium rich, we get a basalt on the top and both, and very magnesium rich rocks called chromatites. Again, for people that don't know the term, it's just a high temperature, very high temperature melt of the mantle. Those reaching the surface are pretty rare. Of course, they're rare, so people, and they're telling us about the early high temperature inside the Earth, so they've been studied a lot. What's going to happen in these stochastics? I'm talking about objects, most of the mass being brought in an object still bigger than 500 kilometers. A 500 kilometer object, when it hits, for the geochemistry we're dealing with, is not much different than dust raining down. It will vaporize the ocean, but still the material and the iron core gets spewed out in a layer all over the surface of the Earth. It gets quickly quenched and reacts with both the steam from the ocean boiling off, and then thousands of years, things cool off. There's not that much heat can radiate quite quickly from the top of the atmosphere, and we end up with the rock being reacted with water. It ends up being hydrous. It's eventually going to get subducted. It's mixed in with oceanic crust, so the material that comes back is going to come back in a basaltic main. It may cover up the existing sediments here. This is forams. We didn't have them in the Hadean, but we probably had calcium carbonate raining down on the surface of the ocean. Anyway, they had the same net effect. Okay, again, the ejecta is distributed equally. We end up with the mixing with basalt, it turns out these highly siderophile elements are like the captain of the ship. When the metal melts, they stay in there rather than evacuating like the stewards would. I apologize to anybody has a relative that's a steward. But again, we have Titanic, watch one night to remember, a night to remember. So the platinum group elements that tag this as being an impact-rich domain are mixed in with basalt. The platinum group element, higher siderophile elements, which are HSC, are going to be mostly from the asteroid because they're mixing in material that's depleted. Material that's mixed into the mantle of the Earth will have a significant more amount to mix with. We also, if you vaporize the ocean and hard vaporizing impact, you'll vaporize the salt also. This will rain out before the water does, and it will collect some platinum group elements. Nice shopping list to look for weird mantle domains. Nobody's found one yet. Again, the object here, you do simple mass balances, and then you do things with the hardcore geochemists and petrologists, and go through all the isotopes and all the periodic table, and tell you a lot more, and tell you whether the kinematic hypotheses are right. Okay, again, the Archean, we probably had episodic plate tectonics on any one ocean. The mantle is hot, you get a large amount of partial melting. It's hard to subduct thick oceanic crust. It's like an oceanic plateau. But once it starts down, the basalt turns into a very dense rock called eclogite, and it goes down. So we're going to have periods. Here, let's go back here. Sluggish subduction. And then once we get started, the whole ocean basin is going to be covered with thin crust. We're going to get stalling here, and we're not getting into forming the earliest crust, so I'm going to go on. Tungsten is the one isotope system I'm going to trace with. It has kind of an optimal half-life for this. Material accretes and forms iron cores early in the solar system. We get the tungsten is isolated from the hafnium, which prefers to stay in the silicate. And we end up with the silicate being very rich in this element, and the core strongly depleted in this isotope. And when it's strongly depleted, here's a bit of exaggeration. We're talking about parts per million relative to terrestrial standards. These are tiny differences, but geochemists have got good at measuring them. The Earth is the reference, it's 0. The Moon is mildly positive. Tungsten's one of these moderate siderophile elements. Some of it stays in the silicate, most of it stays in the mantle. Most goes to the core, a little bit stays in the mantle. Hafnium doesn't want to go into the core at all. And if you take the bulk Earth or the bulk Moon or any other bulk object, to the first order, the isotope systematics are dating the time that the iron and the silicate separated it into big enough iron cores that they were not subsequently disrupted. If we take the primitive early solar system, or no radioactive generation, we take a piece of iron out of iron meteorite where it's never seen hafnium in the last 4.67 billion years. It will have this negative ratio. The average is still strongly negative. So the Earth has mainly, and the Moon in the history, have mainly seen the segregation. Tungsten has formed from mantle silicate material that's segregated very early in the solar system, early compared to this number. And now we start to look at details of the moon-forming impact. This probably occurred after all the hafnium was used up. So the tungsten isotope basically is a passive margin. Okay, in the stochastic model, we have both Theia and Tellus have the same composition. The moon does not accrete much veneer that will bring in more tungsten, so it stays right where it was, and the Earth gets brought down 27 units from accreting the right veneer. And the model here is balanced, and the mass balance does work out. If you bring in all the late veneer with late asteroids, you can get a solution here if the moon and the Earth had the same value when we started bringing in asteroids. If we bring in from Theia core, Dauphin has come up with models like this, and we have to have Tellus be a body that's been thoroughly stirred, so it's not that far off. It has strongly negative ratios at the impact, but doesn't have a lot of tungsten in the mantle. And the Theia would be a body that formed its core very early. Again, we don't know a lot, so to really quantitatively evolve it. And the moon will get proportionally more Theia mantle than the Earth. And many theorists, this is a problem. Here it is a help. The late veneer has little effect. We do get variability. Their current record, I think, is 50, which is higher than the moon. So we could very well in this relatively mild moon-forming impact, where we don't totally homogenize, have material left over that's Theia-rich. And again, there's predictive geochemistry that can be done that can differentiate this from asteroid-rich domains. Okay. We'll just go very quickly here. The Earth cools to a point, rather 10, 20 million years, to where we have a somewhat runaway greenhouse. It's 500 degrees K, 200 degrees C at the surface. At that temperature, carbonates react. Carbon dioxide reacts to form carbonates with basalt, so the basalt will get, CO2 like today will tend to get sucked down into the rock. And the problem is getting it down. At present, CO2 that goes down slabs, some of it comes back, we can see it. We can see subducted organic matter, we can see subducted carbonate from isotopes, but most of it goes down. In the Hadean, it was hotter. It's harder to get it down. But still, with this scenario of rapidly subducting thick, old oceanic crust, it will go down. Again, the tungsten isotopes, we'll skip that. We can use sulfur. It behaves similar to the siderophile elements, but it's also volatile, and it turns out that sulfur, selenium, tellurium behave as a mechanical mixture in the mantle. They also do in sulfur to iridium is very similar in the Earth to the moon. This behaves like a mechanical addition, so we'll go on here quickly. We get to habitability. The key point here is that the Theia core, it's called heavy bombardment. We're stuck with that term, but it's really a weak bombardment. We may have a root to life, and with this stochastic model, which seems of just bringing in the veneer late with large asteroids, the Earth is not inhabitable until the last impact. Skip to the dynamics here, and we get to life, and we'll cut it off with this one. That basically, we've given shopping lifts here for the biologists. that we may get one impact in the Hadean that forms a thermophile bottleneck. By 3.8 billion years, probably 4.1, we have good evidence of that life, photosynthetic life, like modern life, but ones that probably made ferric iron and sulfate with photosynthesis rather than oxygen was present. And we're basically close to now, and some evolution has obviously occurred since then, but we're basically there. And my point is that the late heavy bombardment could be weak. The Earth has lost water in the moon-forming impact, probably around an ocean of it. And there's an anthropic lesson here. We've evolved from animals that crawled out of shallow seas. The Earth has exactly the right amount, not exactly, with a few meters, the right amount of water that we get plentiful shallow seas. And it's no surprise that we've evolved, people speaking and listening in this room, from this type of animal. But it's probably something that there is still somewhat of a stochastic element to this, and we expect to have both water worlds and dunes and other places in the galaxy that we can look at, hopefully. Thank you.
All right, we have time for questions. Anybody?
In one of your first slides, I saw that there's a theory that there's evidence of the small core of the moon, but then almost in the same chart, you said that there was the mantle shows evidence of a large iron core.
So with the hypothesis from getting the core of the moon and the moon mostly from Theia and the mantle of the Earth, that Theia, like the Earth, would have a big core, so its core would have already sucked all the platinum group elements out. So what's more important here is these moderately siderophile elements are also depleted in the moon, and that gives us a constraint on the side of the core. The core size has been measured with seismology and also with the total density and moment of inertia of the moon. People are arguing like 10 kilometers in the radius on what the size of the core is, and out of a radius of 260 to 270, so it's
okay, it's small.
So small, the data may be over-precise, but I think it's pretty evident that the lunar core exists. We don't know what its density is accurately.
Given, given all the stochastic nature of so many of the processes, if you were going to survey Earth mass planets, in the same spot in the habitable zone that we are, how many would you want to see to get a good handle on, based on, what would be your best guess? Would you need to look at 100 rocks to find another Earth, or 10? Or
one would be great right now, but actually get tens or hundreds, then things become easy.
So going back to the idea about where the water came from, you put a number of nails in the coffin about cometary origins. I think you were trying to make the point that the water did come from asteroids?
It has to come either from asteroids, either the ones that planetesimals, but the planetesimal is just basically a glorified asteroid that becomes part of a larger object. This could happen before the moon-forming impact. There's no compositional problem of doing that. There's plenty of water even in the anhydrous classes of asteroids.
So are the DH ratios appropriate?
The DH ratios are appropriate. Comets are wrong.
Okay.
So if you looked at the mantle of the moon and the mantle of the Earth and had no other information, it sounds like you would conclude that the Earth has a small core and the moon has a large core?
We conclude that both have large cores.
Both have.
Because the Earth is also moderately depleted into elements like tungsten, where it's equilibrium. So you, within,
some of the siderophiles
within measurement, the moderately siderophiles are somewhere on both.
Okay.
Anybody else? I have a question. To what extent do we need to worry about how complete differentiation is with respect to the trace elements? Could it be, for example, that some fraction of the tungsten got missed when all of the iron went into the core? Would that complicate the story of saying that all of the tungsten that we have in the crust came from the veneer of impactors after this happened?
Some of the tungsten does get mixed. It would be in the mantle of Tellus and the mantle of Theia, but the idea is it would be in chemical equilibrium with the core at the whatever temperature and pressure that the iron segregated from the air. And there are multiple elements that are not volatile where this can be done with. If you start worrying about details, the process taking a period of time, the process occurring on different bodies of different sizes comes in. But to the first order, the impact is bringing in enough tungsten to change the isotopic ratios within the Theia hypothesis in the Earth's mantle. But it's not bringing in enough to greatly change the absolute abundance of tungsten.
Great. In conclusion, and as a token of our thanks, we, as usual, have our SETI Talks mug to present.
Thank you
as
very
a,
much. I'm honored.
Memento of your time here. Let's thank Norm Sleep.